Hello everyone. Today in this video we are going to learn about the evolution of automation and control systems. So this video is going to be really helpful for people who are working in manufacturing plants. So basically in manufacturing setups or any process, either a PLC or a DCS is used to control the entire process. It is the heart of the plant. So this video is targeted to give a better understanding into what a PLC is or what a DCS is and how a process can be controlled using this equipment. So essentially these terms might be used interchangeably in today's world, PLC, DCS or a controller. So today we'll be learning about how this entire system has evolved, and then we'll know what is a PLC, what is a DCS, and then how do you choose between a PLC or a DCS for your application. So I'll keep posting such videos, so don't forget to subscribe and like this channel in order to get notifications about the latest videos. So let's get started. Here's a very brief timeline on how the entire control system has evolved. So it all started with relays in 1833. So relays is an electrically operated switch which uses an electromagnet to energize or de-energize just the circuits. But of course it has many limitations. For example, it takes a lot of space, and then troubleshooting is very difficult. Even if one relay goes stuck or goes bad in the entire network, your entire circuit fails. So that's quite inflexible in terms of maintenance. So due to these issues, PLC was introduced in 1968, and then further in 1975 a distributed control system or DCS was introduced for a larger purpose. Now we'll see into what these things are in detail. Let's start with the relays. So before PLCs came into existence, as I already said, the only way to control machinery was through the use of relays. So all these relays had to be hardwired in a very specific order, and even if any one relay would have an issue, the entire system as a whole would not work. So essentially the problems were there was a lack of flexibility. You couldn't change the logic of the circuits. If the process requires a change, you need to change the entire wiring of the circuits. Then troubleshooting again was an issue. There was a popular adage at this time, and it goes like this: 5 hours to find it, and then 5 minutes to fix it. It took a lot of time searching for uh, the error or the problem in the circuit. Again, as I said, customization was a big issue. In order to change the process, you needed to rewire the entire circuit, right? So these were the challenges which were being continuously faced by technicians and control engineers. So moreover, most of the companies were facing these issues, but then again, General Motors sent out a proposal in the market. So it issued a request to replace its relay systems. And then there was a team in Bedford Associates who was working on this proposal. And after finding financial support, they formed the company called Modicon. So Modicon worked closely with Bedford to create Modicon 084, which was the first PLC which won the proposal. So that was the first PLC of Modicon, which is in 1968 as shown here. Now let's see what a PLC is. So PLC is essentially a programmable microprocessor device which has been ruggedized for the control of machines, processes, or any other mechanical, electrical, or electronic equipment. So if you know what a microcontroller or a microprocessor is, so it's a bigger version of a microprocessor. So you can build logic and program the PLCs as per your needs. And along with PLC, a few years later came the entire SCADA system. SCADA stands for Supervisory Control and Data Acquisition. So SCADA comprises of four things, which we'll also understand through the architecture, which is a human-machine interface, which is generally in the form of a PC from where you control the entire process, and then the supervisory system, which is the server itself, where all the signals are logged continuously, and then the programmable logic controller, the PLC, which is the controller or the microprocessor, which is easier to understand, and then the communication infrastructure. This is the entire SCADA architecture, as you see on the screen towards your left. So the entire automation is in two levels, level 0 and level 1. Level 0 is the instrument level, so you have sensors, tap switches at level 0. So these are basically instruments which are sending out signals or receiving signals. And then you have the PLC here, and then this is a controller, as already explained. This is also termed as a controller, and all the signals are being sent to this SCADA server. Server keeps storing all the signals, and these signals can be seen in terms of whichever way you want to visualize in HMI computers. HMI is a human machine interface from where the process is controlled. So this is briefly what comprises a SCADA system, and PLC is a part of SCADA. Generally people are quite confused what PLC is and SCADA is, and many places you will also find this HMI called as the SCADA, but only because HMI is the visible part people call it as SCADA. But SCADA essentially comprises of the entire thing as shown in the architecture. It comprises of the HMI, supervisory system, the server, and the PLC. That entire system is SCADA. Now let us look into the architecture in detail. So first I'll explain this entire architecture, then we'll see what kind of modules are there. So as you see in the picture at the center, here's a controller. This is a PLC, and the way it communicates is there are certain manufacturers, I mean all the manufacturers, which have different modules to receive inputs or outputs. So for example, here you can see there is DI, DO, AI, DP and AO. So DI is nothing but digital inputs. It's a module which is used to receive digital inputs from the field or instruments. Again, DO is digital output. This is used to send digital outputs to the instrument. Again, similarly, AI is analog input, AO is analog output, and DP is digital pulse. It is another type of input which is received by encoders. So let's say for example, if you want to operate this proportional valve, V1 is the valve. So in the HMI, you will set a set point. Let's say it's an analog valve, so you can either choose to open it 100%, 10%, 20%, whatever you like. So as per the process requirements, the operator sets a set point 60%. Now this signal goes into the controller. The controller processes it, sends it to the AO, analog output card. This generates an output which can be in the form of 4 to 20 milliamps or 0 to 20 volts, whatever is the control signal requirement, and that signal is sent to this valve, and this valve operates. That is the general flow of the signal. Similarly, if I were to explain how this motor would operate, so an operator here from the HMI can press a button to send a signal to the controller. The controller will then send a signal through a digital output. Now because here is a relay, you need a digital output to energize this relay, on the basis of which this motor is switched on. Right. Also you can have digital inputs. So these are inputs, as in these are push buttons. So you can have a push button which is for motor on, and as and when the operator pushes this button, the input is received. The controller checks for the necessary interlocks, such as you can have interlocks such as the temperature of the motor should not be high, the valve in front of the, if it's a pump, the valve should be open. So such interlocks can be there in controller, and controller will check for all those interlocks and then send a digital output command through this relay to the motor, and then this motor starts running. Again, for switching it off, an operator will press this motor off button. The input signal is received by the controller and sent to the motor again. I hope this is clear. Now these are hardwired signals which are generally in the form of 4 to 20 milliamps, or output can be in terms of volts also. Now again there are so here I have explained the types of modules which are analog input output, digital input output. Again there are digital pulse counters, which is DP, sent by encoders for measuring the speed of motors, and RTD is to measure the temperature, and then there are different types of communication modules to act as a interface for different protocols. Now again there are device protocols. So these are very standard protocols which are supported by a wide variety of devices. Profibus was one of the most widely used protocols. It is based on RS485. So it simply communicates with the motor. So there are many VFDs which can be controlled using Profibus devices. There are encoders, and similarly there are many number of devices. So as Profibus is a protocol, I'll be posting another video in detail what is a Profibus protocol. Similarly, there are Modbus, DeviceNet, Ethernet, Profinet, HART, and Fieldbus protocols. We'll look into a detail in these protocols in later videos. Now, moving on, next is DCS architecture. Now, DCS is simply a advanced version of PLCs. PLCs are centralized into one location or one process, but DCS stands for distributed control systems. I mean, the system is distributed in nature. There can be many PLCs in different areas, and a DCS is controlling. DCS comprises of the entire setup, right? And also a DCS has additional features like controllers can communicate amongst each other, and then DCS has capabilities to process large number of analog signals. So we'll look into those features in the further slides, but just how it is configured, let us look at the architecture. So first, at the base level, there are instruments and devices. So there can be different types of instruments. Again, there are controllers. Now there is communication between these controllers and devices. Now as you see, there are different areas and there are different controllers in these different areas, right? And these can be for different purposes, like they can be controller for controlling a process. Again, there can be another controller for energy management. There can be another controller for a power automation system. So these all controllers keep sending the signals to a server, right? All these signals are stored in server, and this server is also connected to something called as plant network. So in this network, there are HMI stations, engineering clients, and administrators, which can access the data which is being recorded by these PLCs. So these form the control center in the plant. So in a plant, all these HMI stations are uh, are there in a control room, from where the operators or engineers monitor the entire plant, right? And then the next layer is enterprise layer. So you can have an enterprise server, and then your high level executives or managers can look through the essential data through their laptops. Also, ERP can be a part of this enterprise network. So your ERP can directly communicate with your DCS through all these layers, right? I hope this is clear. Now again, this is company specific DCS architecture. This is the architecture of ABB. So ABB has this controller series AC800M. So as I had explained in the earlier slide also, there are instrument at the lowest level, and then there are controllers, and then controllers are connected to a server. Now you see here there's a base system server, and all these controllers keep sending information to this server. And again, this is the plant network, and there are operator stations, extended operator workplace. This is placed in the control room, and as you see, this is the enterprise layer where it can communicate with SAP, IFS, etc. So this is a very broad and bird eye view of a DCS architecture and how it is set up, right? Moving on to the comparison of PLC versus DCS. Let us understand what is PLC more suitable for and what is DCS more suitable for. Now, which applications are good for a PLC? So PLCs are typically suited for applications which have dedicated single machine control, large number of digital and limited number of analog signals. So PLCs, you can think of as a smaller version of what a controller for a DCS is. So it can handle large number of digital signals, but it has limited number of analog signals because the memory and space and RAM is lesser in size as compared to a controller for DCS. Again, sequential control applications which are suited for a single process is good for PLC. PLCs are also good to operate in outdoor locations and extreme conditions, right? And again, when it comes to coordinated control like in motion control, VFD, or a servo motor, PLCs are well suited for those applications as well. So as we talked about sequential control, packaging machines, case packing, labeling and filling machines, etc., have sequential control, in the sense that the sequence is defined and the same sequence is repeated again and again. There is not much of a change in the process. So that is why a PLC is well suited for these applications. Again, applications like radar tracking and solar panel ranges are also very typical applications which do not require much of a customization or a daily change. Also, these are outdoor locations and they're in extreme conditions. So PLC is more rugged in its nature and hence is well suited for these applications. Now let's see what applications are good for DCS. When it comes to DCS can control large number of analog IOs. It can handle multiple PID controllers. Of course, a PLC can also handle PID controls and analog IOs. But then, as I said, you cannot load a PLC much more. So if you have a large number of PID controls and analog input outputs, it's better you go for a DCS. Again, the loading of the controller comes into picture here. Again, when you have cascaded control loops, so as the logic gets bigger and bigger with these and the memory requirements get bigger, you switch to a DCS. So also the next thing is presenting large size data. So it's more visual, and the visualization features of DCS are far more wide and customer friendly, user friendly when it comes to DCS. So whenever you need a multi-screen capability, centralized control rooms, high performance graphics, alarm management system, and you need to analyze historic trends, DCS is the way to go. Again, DCS supports top to bottom redundancy. You can have redundancy at HMI level. So if one HMI goes faulty, you have the another redundant HMI functioning. Same way you have controllers, networks, field bus, and IO cards. Generally, generally in oil and gas industries, redundancy is the utmost requirement because failure can incur huge amount of losses. So there, at all levels, redundancy is maintained. Again, coordinated control, because different controllers need to communicate with each other whenever a application is large or a plant is large. So you have different processes and different controllers controlling those processes. So it's important that the PLCs communicate with each other. And lastly, system and network management. A DCS system integrates easily with ERP, document management system, other PLCs, and field bus communications like Modbus, HART, TCP, IP, etc. Of course, these field bus communications are supported by PLC as well, but when it comes to large scale integration with ERP and stuff, DCS is more favorable. Now, how do you make a choice between a PLC and a DCS? So you see here on the top, there are some DCS core applications and then some are PLC core applications, and then there are gray areas in between where depending on the scale and size of the application, you can choose whether you want to go for a PLC or a DCS. Now, if you see in the DCS core applications, it's oil and gas, petrochemical, metals and mining, power generation, pulp and paper. So one thing that you can make out is the size of the applications is very large. The number of inputs, outputs are very large, and the processes are very distributed in nature. Henceforth, these are DCS core applications. Again, if you see PLC core applications, these are smaller applications or sequential applications or applications which do not need much of a change. Right. So how do you choose? So basis on the size and requirements, if your size is really small and the application requirement is really small, go for PLCs. One more step ahead is process PLCs, which have analog capability as well. So if you have some few numbers of PID controls, you can go for a process PLC as well. Again, then further stepping up, you can have small DCSs for process control, and if the size of your application is really large, you go for a large DCS, which is essentially process automation system. So what has happened over a period of time, PLC manufacturers are trying to incorporate more and more features to be able to come closer to what a DCS is. So they are also improving the size and memory and RAM of their PLCs so that they can incorporate more and more requirements. Now DCS, when it came, it was quite expensive. So even DCS manufacturers are trying to make it lesser expensive and be comparable to what a PLC is. So in these days, mostly you will see there are many PLC controllers which are compatible with a DCS as well. So for example, ABB has controllers which can work as a PLC and a DCS as well. So there are many gray areas. It's not strictly defined in today's day. Well, thank you. That was it. I hope you have a better idea on what a PLC is and what a DCS is, and you are in a good position to choose whether you need a PLC or a DCS for your application. If you have any queries, you can post it in the comments, and I'll be more than happy to answer your queries. Thank you.